In our early stage of studying chemistry, we were told that matter undergoes changes, and these changes matter undergoes can be classified under physical changes and chemical changes. And in these physical changes, new substances are not formed, whereas in chemical changes, new substances are formed. Mark the word. I'm going to make use of this one and the point 4 of the differences as you see on the screen. The point 4 reads that during physical change, no heat is involved except if we are discussing something like latent heat of fusion and latent heat of vaporization. But when we are discussing about chemical change, at every chemical change, there is heat change. But my question here is, why is it that we have heat change whenever we have a chemical change? The simple thing can be explained if we understand that every chemical substance possesses what we call heat content. What I mean by this heat content is the amount of energy in form of heat that is being possessed by the chemical substance due to its physical state and its structure. Here we have the reactant will have its own specific heat, the product will have its own specific heat. If for instance we have something like substance A reacting with substance B to give us substance C, and substance A, as you can see on the screen, is 20 kilojoule, substance B, as you can see on the screen, is 30 kilojoule, and substance C, as you can see on the screen, is 40 kilojoule. You're going to understand that if we are having a balanced chemical reaction with this A plus B to give us C, this point that A heat content added with B heat content is supposed to give us 50 kilojoule, and that of C is 40 kilojoule. You will notice that there is a change here. Pause here. Let's go back to physical change. Here I just demonstrated something we call chemical change. If we have a physical change, remember they say that no new substance is formed in physical change. Therefore, we are going to have something that looks like this. A plus B will give us A plus B because there's no new substance formed. Hope you get that. Now we are going to have 20 plus 30 to give us 50. If you go over to the product side, we are still going to have the same thing, 20 plus 30 to give us 50. As far as we have equal heat contents, we are not going to have any change. But when we are dealing with chemical change, you notice that we have 20 plus 30 to give us 40, which is abnormal. Therefore, what we are going to do is to compensate heat content by assuming that there is a loss of heat to the environment. This illustration that I gave out here is actually what we call exothermic reaction, because at the product side, the product heat content is less than the reactant heat content. Just look at it. We have 50 here and we have 40 here. You notice that the difference between 40 and 50 is going to be what? 10. Therefore, we're going to compensate the product heat by adding plus 10 kilojoule, but this plus 10 is not going to be under any substance, but will be evolved to the surrounding. Therefore, whenever we have a reaction in which there is a release of energy in form of heat, we call this reaction exothermic reaction. And when we have a reaction when there is an absorption of heat, we call this endothermic reaction. We are to look into examples of exothermic reaction. For instance, if you are in your school and your teacher presents to you something like tetraoxosulfuric acid, hydrochloric acid, or triazonitrate 5 acid, and asks you to mix water with it. Here we are going to add the acid to the water. First of all, we are going to use our hand, touch the test tube where the water is. You're going to notice that the water is normal. But when we add the acid to this test tube, we are going to notice that the test tube will feel hot. The feeling of hotness is just like that 10 kilojoule that we saw when we have A plus B to give us C. That 10 kilojoule is not the heat content of any substance, rather it is being released to the surrounding. That is why anything that is around that surrounding will feel hot. That is the example of exothermic reaction. Another way we can see exothermic reaction is in displacement reaction. We can see that also in combustion reaction and neutralization reaction. If you want to check for endothermic reaction can be demonstrated when we have something like sodium chloride, ammonium chloride. We can even have that also in potassium triazonitrate 5. That one, whenever we put those salts inside water, we are going to feel cold. the temperature of the test tube will still be lower than it was. It is because in endothermic reaction, heat is being absorbed. That is to say, we continually give heat to endothermic reaction. It will be good to introduce the energy profile of a chemical reaction. Whenever we have a chemical reaction, we know that there's going to be a heat change, and we can actually demonstrate it using graph. I want you to look closely to this graph here. This is actually the pathway of the reaction, when the reaction starts and when it ends. Here we have the energy levels here, as you can see this side. Okay, look at this. We have two types of energy profile, one for exothermic reaction and one for endothermic reaction. This one you are seeing here is one for exothermic reaction. The question can be, how will I know that this is exothermic reaction? To know that this is exothermic reaction, you need to look at the energy level of the reactant. Is it higher than that of the product? Now look over here. We have this as the reactant, then we have here as the product. What about how to identify whether this thing is endothermic reaction? Therefore, if you want to understand if this thing is endothermic reaction, what we are going to look at is energy level of the product. Is the energy level of the product higher than that of the reactant? Look over here. Using the diagram again, the reactant is at this position and the product is at this position. Therefore, if we subtract these products and this, we are going to have endothermic reaction, which is going to give us a positive sign, because the energy level of this product is higher than that of the reactant. And if you look at this, you're going to notice there's a place around activation energy. And the activation energy is that minimum energy that is required for a reaction to occur. And this activation complex or transition state is that particular point in which the material or the reactant is about to form the product. We call it activated complex. It is actually a transition state, as we have the initial state and the final state. Where the initial state is the reactant side and the final state is the product side. And we have this activated complex to be the transition state. We have heat of reaction. Heat of reaction is the amount of energy in form of heat that is being absorbed or evolved when molar quantities of substances react according to the representation of chemical equations. And inside this, we have something like heat of formation. We have something like heat of neutralization. We have heat of combustion. We have heat of solution. Let's treat them one after the other. Let's start with heat of formation. Heat of formation is the heat either evolved or absorbed when 1 mole of substance is formed. Here you will notice that I say either absorbed or evolved. That is to say that heat of formation can either be endothermic reaction or exothermic reaction. We have to define it based on standard heat of formation. What we just need to put over there is that this reaction was done under standard conditions. Standard conditions we mean here include 25 degrees Celsius, 1 atm, and 1 mole of the reactant. For heat of combustion, what we mean by heat of combustion is the amount of energy in form of heat that is being evolved when 1 mole of a substance completely burns in the presence of oxygen. And when this is being done under 25 degrees Celsius and 1 atm, we take it to be a standard heat of combustion. Example of that can be seen when coal burns in oxygen to give us carbon 4 oxide, or even when we have something like ethanol burning in oxygen to give us carbon 4 oxide and water. If you notice from that heat of combustion, you will see that I made use of the word evolve. That is to say there is heat coming out from the reaction mixture to the surrounding. That is to say the surrounding is going to feel hot. What type of reaction is that? Exothermic reaction, because heat is being released to the surrounding. Well, let's look into heat of neutralization. Heat of neutralization reaction is the heat evolved when 1 mole of hydroxide or hydroxide ion from a base completely neutralizes 1 mole of hydrogen ion from an acid to form 1 mole of water. Mind you, if we are doing this thing under standard condition, you know what I mean by standard condition, 25 degrees Celsius and 1 atm, that means that we are going to call it standard heat of neutralization. And if you look at it again, I made use of the word evolve, telling you that it is a exothermic reaction. That is to say, combustion reaction and neutralization reaction are examples of exothermic reaction. We still have heat of solution. What we mean by this heat of solution is that amount of heat that is either evolved or absorbed. When it is acid dissolving in water or when it is base dissolving in water, it is heat evolved. But when it is something like normal ionic salts like ammonium, chloride, potassium nitrate 5, as you can see, as I said previously, these ones are actually endothermic reaction, whereas that of the acid gives us exothermic reaction. Now, the heat evolved or absorbed when a solute dissolves completely in a solvent. We call that heat of solution. And when it is being done under standard condition, you know what we're supposed to call it? Standard heat of solution. And according to the first law of thermodynamics, it is believed that energy is neither created nor destroyed, but can be transformed from one form to another. I want to show you something. When we are discussing this, there is something that is very, very important and crucial here. What do we actually mean by this first law of thermodynamics? We believe that the change in internal energy is equal to the heat absorbed by the system and the work done by the system. One thing about this first law of thermodynamics is just focuses its attention towards heat absorbed and heat released to the environment. It does not tell us is how spontaneity is this reaction going to take place. That is why we go for the second law of thermodynamics to see if it is possible for us to predict the spontaneity of a chemical reaction by looking at the chemical energy or the heat energy of the reaction. The second law of thermodynamics tries to solve the problem by telling us how to predict if a chemical reaction is going to occur. How does it predict? It states that for the spontaneity of a chemical reaction, there must be increase in the entropy of the system. What do we mean by this entropy? Entropy of the system is the degree of disorderliness of the system. For instance, when we have something like solid, you know, solid has a particle well packed or arranged, different from how liquid look like and different from how gases look like. Gases, they have a higher tendency to move randomly than the liquid. That is to say that the gas has higher disorderliness compared to liquid, the same way the liquid is having higher disorderliness compared to solid. Therefore, we can use this to predict whether a reaction can actually happen or not. And the relationship between this entropy and heat change is shown as change in entropy equal to change in heat all over temperature. That way we can actually do some calculation on this, but wait, the calculations comes after. There is a driving force that causes chemical change, and this driving force is what we call free energy. And this free energy must be there for a chemical reaction to occur. And we have a relationship between this free energy, entropy, heat change, and temperature. As you can see here, change in G, we call it change in free energy, is equal to change in heat content minus temperature multiplying change in entropy. This is a relationship between the free energy, the heat content, entropy, and temperature. Okay, let's look into some calculations involving this heat of reaction. You can see the question on the screen, and we have to work on this. But before I answer this question, you need to understand what we mean by bond energy. Bond energy is that average amount of energy required in breaking or forming a bond. That is to say, the amount of energy required to break a bond is the same amount of energy to make that bond. And you need to understand that in chemical reaction, for it to occur, there must be a breaking of bonds, at the same time, a formation of bonds. The question is, calculate the approximate heat of reaction of the following reaction from the given bond values. That is to say, as you can see on the screen, the bond values. Okay, we have hydrogen-hydrogen bond to be 435 kilojoule per mole, and we have hydrogen-oxygen to be 464 kilojoule per mole, and we have oxygen double bond oxygen to give us 498 kilojoule per mole. At the reactant side, what happens there is that bonds are broken, but when we go to the product side, we are going to notice bonds are formed. And for us to be able to calculate the energy required, what you just need to do is to say reactant plus the product. The energy gives us what we are looking for. Let's go with this. At the reactant side, we're going to have bond broken. Bond broken. Hope you get that. Okay, you have there 1 mole of hydrogen-hydrogen bond that is being broken. As you can see the value. And since you know bond broken is endothermic because we are giving energy to break that. Hope you get that. Okay, we go again. Half mole of oxygen-oxygen bond is a double bond of oxygen. We have that as 249, as you can see demonstrated. If you go to the product side, you know at the product side what happened here is that bonds are formed, and when bond is being formed, energy is being released because it is exothermic reaction. That is, formation of bond is actually done by exothermic reaction. We have here 1 mole of hydrogen, oxygen, hydrogen, and in this 1 mole of hydrogen, oxygen, hydrogen, we are having 2 moles of hydrogen oxygen bond. You have something that looks like this, OH, and also another OH. Despite it's the same O that is bonding the OH and the other OH. Hope you see that. Therefore, we are going to have the value to be 2 times minus 464, which is going to give us minus 928 kilojoule. Therefore, when we combine the broken bond with the formed bond energy, we are going to have the value to read as 684 kilojoule minus 928 kilojoule, which is going to give us minus 244. You wonder why is it minus? Remember that exothermic reaction always end up being value in negative, and endothermic reaction end up being value in positive. And we say that bond broken is endothermic and bond formed is exothermic. I hope you get that. And bond broken, we see it at the reactant side, and bond formed, we see it at the product form. Because at the reactant side, bonds are being broken, but at the product form, we are forming. That is, in a chemical reaction, we know we have rearrangement of atoms, rearrangement of bonds. Bonds are broken and bonds are what? Formed. And I want you to understand, whenever we have this bond broken to be very, very larger than the bond formed, we have a endothermic reaction. But whenever the bond broken is less than the bond formed, we have what we call exothermic reaction. Calculate the change heat of a chemical system when the entropy is 218.2 kilojoule per Kelvin per mole, and the temperature is 100 degrees Celsius. Notice that this 100 degrees Celsius is converted to Kelvin to give us 373 Kelvin. And the formula goes with change in X equal to change in H all over T. The T here is temperature, and H here is heat, and the S here is entropy. Now, if we make the change in heat the subject formula, we are going to have change in heat equal to temperature times change in entropy. And we know our temperature to be 373, and we know our change in entropy to be 218.2. Therefore, if we multiply it together, we are going to have 81.4 kilojoule. Let's go for the third question. Calculate the bond energy of ethanol and prove that burning of ethanol to form water and carbon 4 oxide is an exothermic reaction. Solution. Note that bond energy of ethanol can be gotten by calculating the number of times carbon bond with oxygen carbon bond with hydrogen, hydrogen bond with oxygen, and carbon bond with carbon. I want you to understand how to calculate the number of bonds of this CC, CO, CH, HO. For instance, if we have here, if you look at ethanol, to express ethanol, what we have here is C, bond with OH, bond with CH, and CH. As you can see. Okay, now if you look at it again, how many places do you see carbon bonding with carbon? We have only this and this place. Therefore, we have only one carbon bond. We go again. How many times do we see carbon bonding with hydrogen in this my expression? Look over here, we have carbon, hydrogen, 1, carbon, hydrogen, 2, carbon, hydrogen, 3, carbon, hydrogen, 4, and carbon, hydrogen, 5 places. Now, since we have that, we have 5 moles of carbon, hydrogen bonding. How many places are we going to see carbon bonding with oxygen? We have only one place, carbon bonding with oxygen. And how many places are we going to see oxygen bonding with hydrogen? We only have one place, OH. Now, if you check out that value, you will see how I got my value for the bond energy. The bond energy from this gives us 3,241 kilojoule. That is just the bond energy of ethanol. But mind you, the bond energy of ethanol is equal to the amount of energy in form of heat that can be used to form the bond or even to do what? Break the bond. Since this ethanol is going to participate in a reaction with oxygen, that means that it is going to be broken. It's going to be a bond broken, which is going to be what? Positive. Now let's look for oxygen. How many oxygen are we seeing in this place? You see, I have here 7 all over 2 oxygen bond. You get me? Now, you know each oxygen bond, the value. That means we're going to multiply it by 7 all over 2 to give us the value. Now, the bond of the ethanol, which we have gotten from this place, added to the bond of the oxygen, will give us 4,984 kilojoule. And they are endothermic reactions. Therefore, they are going to be positive. And we need to add it up to the bond form. Now, let's go for the bond form. That is, you know, when this ethanol reacts with oxygen, it's going to give us carbon 4 oxide and water. If you look closely to the carbon 4 oxide, it is carbon, oxygen, and this is double bond, and this is double bond. That means that we have 2 carbon oxygen double bond in carbon 4 oxide. From the equation here, we are having 2 moles of carbon 4 oxide, which means that we have 2 carbon oxygen bond times 2, which is 4 carbon oxygen bond, as you can see over here. The value. Now, for the water, we have 3 moles of water. And if you look at how water is arranged, it is hydrogen, oxygen, and hydrogen. You notice that it is hydrogen oxygen bond, oxygen hydrogen bond. We are going to have 2 hydrogen oxygen bond per 1 molecule of water, but we have 3 molecules of water. Therefore, we're going to have 6 moles of hydrogen oxygen bonds here, as you can see. Now, when we sum the answer from this and this, we have minus 5,488 kilojoule. And this value is negative because it is the bond form. What we mean by bond form? Exothermic reaction. We believe that bond form releases energy to the surrounding, whereas bond broken requires energy to be done. When we join this positive value with this negative value, this proves that since we are having minus sign, it proves that this is exothermic reaction, since exothermic reaction value end up being negative signs. Note that Hesnot said that the total enthalpy change of a chemical reaction is the same despite the route followed by the chemical reaction. Thank you very much for watching this video to this extent, and I am pleased to have you here with me from the beginning till now. And I ask you to make sure that you write down things the next time you are watching this video. And if you have a question, don't forget to let me know. And don't forget to share this video. I mean the link. Just click the subscribe button if you have not subscribed to this YouTube channel. And if you have, just click the share button. And make sure you share it on your social media platform for my good and for